Hello everyone, welcome to my channel. This is my second lesson on geometry. In lesson 1, I presented proofs and applications of theorems 1 and 2. Just to remind you, theorem 1, the name is a straight line drawn from the center of a circle to the midpoint of a chord is perpendicular to the chord. Theorem number 2, the name is perpendicular from center to chord. The statement is the perpendicular from center of a circle to a chord bisects the chord. In this lesson, I have 4 theorems that I want to prove. And I'll bring up applications of the 4 theorems I'm going to prove in this lesson here in my third lesson. If you are new to this channel, don't forget to support us by subscribing. So let's start. Theorem number 3 overall, but theorem number 1 in our lesson for today. The name is perpendicular bisector of a chord, and the statement is the perpendicular bisector of a chord passes through the center of the circle. So there is the construction. So we are told that E is the midpoint of BD, which is our chord, and AEC is the perpendicular bisector of BD. So we are to prove that O lies, which is the center of a circle, lies on EC or on AEC. So obviously, as you can see, we assume that the center is not on AEC, somewhere in that position shown there. And then we go on to show that it is not possible that the center can be anywhere else but on AEC. So this is how we prove it. Let's move straight to proof. I am going to capture that circle just so that we're able to get it on one page. Let me just remove the other pages here that may not be useful at this stage. We're gonna pick this one at a later stage. So theorem number 1 in our video for today, but overall theorem number 3. So I'm gonna write this as number 3 because we wanna make sure that we take all the theorems from number 1 up to the last one on circle geometry. So this is what we have. We have a small circle, and we're required to show that if that is our chord, and this is the perpendicular bisector of that chord, let's call it A as it's indicated here. AEC, as you can see, I'm going to call this one E, that point there, and that's C, but that's B, and that's D. So we are required to prove that O, which is the center of this circle, lies on AEC. We assume the center is not there, but is somewhere in that position. And so that is our construction. As you can see, basically, I'm taking it from here. As you can see, right? So this being a theorem, we remember we start by saying given. So given, what are we given? We're given circle A, B, C, D. What do we know? We know that with E on BD, such that AEC is the perpendicular bisector of BD. That's what we're given. We're given circle A, B, C, D with E on BD such that AEC is the perpendicular bisector of our chord BD. So basically we're saying that part equals that part. Let's number these angles 1, 2, 3. Obviously that angle is 90 because we are told that AEC is a perpendicular bisector. Right, so what do we do then? Well, we go straight to what we're required to prove. To prove that, or required to prove, what are we required to prove? We are required to prove that O, the center, O of the circle A, B, C, D lies on A, E, C. This is what we're required to prove. Do we need construction? Yes, construction. As you can see there, what are we saying? Assume or suppose. Assume or suppose center O is in the position shown. Not on A, E, C. We assume the center O is in the position shown, and that O is not on A, E, C. Now, let's go straight to proof now. Proof. Basically, you can see that angle E1 has to be 90 degrees. Why should E1 be 90? I'm going to do this here, showing that E1 is 90. Why should E1 be 90? Because remember, theorem number 1, we said a straight line from center to midpoint of chord is perpendicular to the chord. So here we're going to use the name of theorem 1. So here we're going to say a straight line from center to midpoint of chord. That's the reason. Right? We also know E3 is equal to 90 degrees. How do we know? This is given. Remember, we're given that AEC is a perpendicular bisector of BD, so which means that angle 3 is actually equal to 90 degrees. So we also know that E1 plus E2 plus E3, this must give us 180 if we add them up. Why? Because these are angles on a straight line. Remember, BED is a chord, and therefore it has to be a straight line. And therefore, when we add up all the angles on it, we must get 180 degrees. Now, let me put E1 and E3 together. So E2 plus E1 plus E3, this is equals 180. But this one is 90 each. So we're going to say E2 plus 90 plus 90 equals 180. Clearly, you can see that E2 is 0 because when you subtract 180 from both sides, this is 180. These two angles add up to 180. When you subtract 180 from both sides, you can clearly see that E2 equals what? 0. So let's go back to the diagram. The only way that E2 can be 0 is when OE coincides with AEC, and therefore O must be on AEC. And that is how we prove it. So we're going to say, therefore, from here, because E2 equals 0, we can say OE coincides with AEC, and therefore O lies on AEC. This is how we prove it, and we can simply say QED at the end there if you are interested in doing that. Basically, which simplifies, or it means as required. So we've managed to prove that O actually lies on AEC. This is the end of theorem number 3. Let's move on to theorem number 4. And theorem number 4, here it is. Basically, it says the name angle at center is twice angle at circumference. The statement, the angle that a chord subtends at the center of the circle is equal to twice that which it subtends at the circumference. So we are basically saying, here's a construction. We are basically saying we need to show that angle AOC, this angle here, angle AOC, that angle is twice that angle there. This angle at the center is subtended by a chord AC or by arc AC. And this angle must be twice the angle that the same chord or arc subtends at the circumference. Now, how do we prove it? Well, you can see the construction here. Basically, we construct BO produced to E. That means we draw BO and we stretch it or extend it, maintaining it as a straight line to E. That is critical for you to know. The word produced means extended and maintained as a straight line. So we form angles A1, A2, B1, B2, C1, C2, and then we have at the center, we're just going to name the two angles of interest, O1 and O2. And then we look at this triangle here and look at that triangle and use what we call exterior angle of a triangle and go on to prove it as follows. Going on to page 4, and if you allow me to do as I've done in theorem number 3, I'm going to redraw the circle but make it a bit small so that we fit the proof totally in there. So what basically we're saying is this is what we have. That's our chord. That chord subtends that angle at the center, and we're interested to show that the angle it subtends at the circumference is actually half of the angle at the center, or the angle at the center is twice angle at the circumference. The construction, remember, like we said, you draw BO produced to E. You can put E anywhere. Just going to maintain it the way it is indicated in the diagram. So these are O, and remember these must be radii and they must be equal. Numbering of the angles, we have numbered these angles as follows. We've called this one 1, and that's 2. Up there we've called this one 1, and that's 2. Here we've called this one 1, that's 2. And here we've called this one 1, and that's 2. So what do we have? We have A, and then we have B there, and C there. Right, now let's go on and to prove it. Right, so our proof will be as follows. And I'm going to call this page 4. I'm going to call this page 4 because the previous page was page 3. Page 4. Right. So basically, we move on to given. So what are we given? And I want to write on the outset, I want to make this angle here have a small letter A. That one also have small letter A. I'm going to explain why that is the case. That angle there, I'm going to give it small letter B. And that angle also small letter B. We'll explain why that is the case. Right, so what are we given? Given circle ABC with center O. That's all we're given. What are we required to prove, or to prove that? We're required to prove that angle AOC is twice angle ABC. You can see in this diagram here, we're required to prove that angle AOC is twice angle ABC. Do we need construction? Yes, we do. Construction. What are we saying on construction? Draw BO produced to E. And then we go straight to proof. And I'm going to say here now, using small letters or using information shown in the figure, above that figure there, we see on the outset that AO is equal to BO is equal to CO is equal to CO. Hope you can see that equal sign there. AO equals BO equals CO. Why is this the case? These are radii. And we know that we constructed that BO there, but radii is sufficient to give us a reason. What else we can say therefore? Therefore, A1 is equal to B1 equals small letter A. Why is this the case? A1 equals B1 equals small letter A, because these are angles opposite equal sides. Remember, this is a theorem in the lower grades, like grade 10. And you can see that this is in triangle AOB. This is what we have. Now moving to the other triangle, BCO or BOC. Also, we can say angle B2 is equal to angle C2 equals a small letter B. Why? Again, angles opposite equal sides. Right, now let's move back to the first triangle, triangle AOB. In triangle AOB, you will agree with me that E1 is actually equal to A1 plus B1. In triangle AOB, A1 plus B1 equals angle E1, angle O1 actually, not E1, angle O1 here. This is angle O1. E is outside there, but I'm focusing on angle O1. Angle O1, let me just write it like this. Angle O1 equals A1 plus B1. You can see it in this diagram here. It's a bit bigger. So we're basically saying angle O1 is equal to angle A1 plus angle B1. And the reason for that is because this is exterior angle of triangle AOB. So the reason for that, exterior angle of triangle AOB. And so what is A1? Well, it's A. What is B1? Well, it's A also. You can see it there. And what is A plus A? Well, this is twice A. Let's move to the other triangle now. In triangle AOB, this is what we have managed to achieve. O1 is actually equal to A1 plus B1, as you can see, and then it translates into twice A. Let's move to the other triangle, triangle BOC. In triangle BOC, O2, this angle here, O2, that angle there. Remember, we focused on this one there at first. Now we are on the other angle there. O2 is actually equal to B2 plus C2. Same reason, exterior angle of a triangle, but in this case we are talking about triangle BOC, of triangle BOC. What is B2? Well, you can see that it's small letter b. There it is, B2 equals C2 equals small letter b, and also C2 is small letter b. Adding these two up, the answer is twice b. So we are now going to say, by addition, we're now adding. What are we adding? We're adding O1 plus O2. The answer must be 2A plus 2B. What is O1 plus O2? Well, let's factorize right hand side first. This is twice A plus B. But what is angle A plus B? If you check in this diagram here, it will be that angle plus that angle. It must be the whole of that angle there, which is angle ABC. You can see it here. That angle, the small a and small b, when we add the two up, we find the total angle there, which is angle ABC. So basically, we're saying that this is twice angle ABC. But what is angle O1 plus O2? You can see it from here. It's even better. O1 plus O2 is actually angle AOC. So this is angle AOC. Angle AOC is twice angle ABC. And that's what we're required to prove. You can see it here. AOC is twice angle ABC. This is the end of theorem number 4. I'm moving on to theorem number 5. Remember, I said I have 4 theorems, so basically I have how many theorems left? I have 2 theorems left now. Moving on to theorem number 5. Theorem number 5 is this one here. Theorem number 5 is this one here. There it is. That's theorem number 5. The name of the theorem is angle in a semicircle. And the statement, the angle in a semicircle is a right angle. Or we can also say the angle which diameter of a circle subtends at the circumference of a circle is equal to 90 degrees. The construction here, so we are given circle ABC in which A or C is diameter, and we are supposed to show that angle ABC, that angle there, is 90 degrees because subtended at the circumference by chord which is A or C, and this chord is a special chord because it's the longest chord. We call it diameter. So we're supposed to prove that that angle is 90 degrees. Well, how do we do it? Well, here is how the proof goes. Going to page 6. This is theorem number 5. Allow me to capture the circle again. It takes us a bit of time, but yeah, let's just go for it. Capturing the circle, we have, there is a small circle, and we are required, we are told that that is our diameter, A, O, and we have C here, and this diameter subtends angle ABC at the circumference. This is our B. We're supposed to prove that that angle is 90 degrees. Well, how do we go about this? This is one of the easier theorems to prove, and we are going to prove it as follows. So, and I'm going to use small letters. If we use a small letter, we call that angle X, and let's call this angle here at the center Y. We're gonna say this is a theorem given. We're given circle A, B, C, in which given ABC, it has to be circle ABC. Let me insert that one there. Given circle ABC in which AC is diameter. And we have our center O there. Right, we can just keep it the way it is. And what are we required to prove? To prove that, we're required to prove that angle ABC equals 90 degrees. Do we need construction here? No, this is one of those theorems where construction is not necessary. We're just going to use theorem number 4. So here we're going to say here, proof straight. And I'm going to say using small letters. And I'm going to say y is twice x. Reason, angle at center. I told you. This is the name, theorem number 6. Angle in same, no, this is angle in same segment. That's theorem number 6. We're yet to prove that. Theorem number 4 is this one. Angle at center is twice angle circumference. This is the name of theorem number 4, and there is a statement. We're going to use that one as a reason for this statement here, where we're saying y is twice x. Angle at center equals twice angle at circumference, right? But we know, but y equals 180. What is the reason for that? Straight line. We know that AOC is diameter, it's a straight line. We can say therefore 2x equals 180. Why? Because both sides are equal to y. 180 equals y, 2x equals y up there. Dividing both sides by 2, you get x equals 90 degrees. And what is x? Is angle ABC, which is equal to 90 degrees. If you like, you can say as required. It's QED. The easiest of the theorems maybe one can argue on geometry to prove. But we're moving on straight to theorem number 6, which is our last one in this video. Theorem number 6, basically it says angles in the same segment are equal. There it is. Angles in the same segment, that's the name of the theorem, and the statement angles in the same segment are equal, or you can also say angles subtended by the same chord or arc at the circumference of a circle are equal. Angles subtended by the same chord or arc, you can say angles subtended by the same chord BC, in this case in our construction here, or arc BC, angles subtended by arc BC or chord BC at the circumference of a circle are equal. Basically, we're talking about in the opposite segment. We have two segments here, the minor segment down here, this one, and the major segment, the top one there. And these angles must be at the circumference. Otherwise, the two angles will not be equal. How do we prove this? Well, we need construction. You can see here, we're drawing radii, BO, and CO. And basically taking advantage of theorem number 5, which says the angle that a chord subtends at the center of a circle, theorem number 4 actually, the angle that a chord subtends at the center of a circle is equal to twice the angle that it subtends at the circumference. So angle at center is twice angle at circumference. Theorem number 4, if you go back to the video and check the theorem number 4, that's the one we're applying here. So let's go straight into proof then. Now, like I've done in the previous theorems, I'm going to redraw the circle just to have everything on one page, right? And we're basically saying we have a chord here. This is our chord BC. It subtends that angle there, D, and it also subtends that angle there on the other side at the circumference, obviously. Let's call that angle A. We are required to prove that these angles are equal. Let me use small letter a here and small letter d there. And we have our construction. There you go. Radii. Right. There you go. Basically, we're saying that point there is our center. And I'm going to have that angle. I'm going to call that angle. I'm going to call it x. The angle at the center. So it's a theorem. So we say given. What are we given? We're given circle ABCD. That's all we're given. Nothing else. What are we required to prove? We're required to prove that, watch this, angle A, I'm going to just call it A because that's only angle made at A. So angle A is equal to angle D. Do we need construction? Yes, we do. Construction, we're going to say draw radii, plural of radius, BO and CO. Proof, again, I'm going to say using small letters. I can say x equals twice A. Angle at center equals twice angle at circumference. Also, x is twice d. Same reason, angle at center twice angle at circumference. You can clearly see that this chord here, let me use my 2 pens here, this chord BC subtends that angle at the center. The same chord BC subtends that angle at the circumference. So therefore, the angle at the center is twice the angle at circumference. We can also say the angle at center is twice the angle at circumference on the other side there. And then I'm going to say, therefore, 2A equals 2D because they are both equal to X. As you can see here and there. Cancelling the 2's, A equals D. But what is A? Well, A is angle capital A. What is D? Is angle capital D as required. Code erat demonstrandum. End of proof for theorem number 6. Like I said at the beginning, in my lesson number 3, I'm going to come up with questions involving applications of the 4 theorems I've proved in this video. And then I'll move on to lesson 4. I'll be bringing in another set of theorems until we complete sacred geometry. If you are new to the channel, support us by subscribing, sharing these videos with friends. Your feedback is absolutely necessary for us. It helps us to plan on how we present this information to you. All right, I'll see you next time.